Hello lovelies, in this video we're going to go through our AQA GCSE Physics Separate Science Higher, the paper one that we've written for 2024. So what we want you to do is to pause after the question comes up, have a go at it yourself and then play the video and watch us work through the answers together. Look at how we structure the maths questions, look at how we answer the 6-mark questions, and then take these skills through into your exam.
Light-emitting diodes have many uses. They're used in many electrical devices, including remote controls and traffic lights. Here we're asked to describe what a diode actually is. And this is a little definition that we need to know, so if you don't know it, get yourself out a flashcard now and copy it down with me. So a diode is a component which only allows current to flow in one direction. And that's all we need to write down there to get our mark. In this question, we're talking about light-emitting diodes. So if we were asked about a light-emitting diode, then we would still give the same definition, only we would add that light is emitted in this process too. Next up, we're asked to describe the energy transfer that occurs in an LED, a light-emitting diode, when it's connected to a circuit with a power supply. So here we need to know what it begins with, and of course initially it's connected to a power supply, so it has electrical energy to begin with, and then it transfers it to light energy, and that's why it can emit light. So we can say that in a sentence, or we could write it like I have here, but you would get your 1 mark either way. Now we're asked to sketch the IV graph for a light-emitting diode. So there's a few of these that we need to know off by heart, perfect for flashcards. For a light-emitting diode, or any diode for that fact, the current stays very close to zero for negative potential differences, and only when it becomes a positive potential difference does it begin to increase. And then it increases with an increasing gradient. And don't forget, the reason why it stays so close to zero, that current, for negative potential differences, is because of that definition of a diode, the fact it only allows the current to flow in one direction. And we're seeing it here in this graph. So here we have a big 6-mark question. We're asked to describe an experiment that will find the IV graph of a light-emitting diode. And we can use a circuit diagram in our answer, and I think they're a really useful way to aid our explanation. So let's start off by drawing our circuit diagram. Now, the first thing I'm drawing is the symbol for a light-emitting diode. So what we have here is this triangle with a line against it with 2 arrows pointing away. That's because it's a light-emitting diode. A diode alone wouldn't have those arrows. Then we have that diode connected in series with a power supply and also an ammeter. Then we're going to place a voltmeter in parallel. Now, the reason why we have that ammeter is to measure the current in this experiment. And we always want to have ammeters in series with the component that we're measuring. So then we also have a voltmeter, which is the circle with the V in it. Now, voltmeters always need to go in parallel with the component that we're investigating. And the whole point of a voltmeter is to measure the potential difference or the voltage in the circuit. So there's one last thing that we need to add to this circuit diagram that we're missing at the moment. So we need to have a way to vary the potential difference. And the way that we're going to do that is by adding a variable resistor. A variable resistor looks like a rectangle with a diagonal arrow going through it. So now we've got this circuit diagram set up, and by drawing it and labelling it well, already actually we've got quite a good chunk of these marks in this question. So now let's describe what we're going to do. So once we've set up the apparatus in this way, we're going to record the potential difference and the current. Once we've done that, we're now going to use our variable resistor to change the potential difference. Once we've done that, we're now again going to record the new potential difference in current. Again, we're going to use our voltmeter to measure potential difference, and we're going to use the ammeter to measure the current. Now we're going to use that keyword that we use in so many of these investigation questions. We're going to repeat this process, because the more we repeat it for slightly different potential differences, the more data points we'll have for our graph. Now, once we've done this, we'll notice that we're only getting positive potential differences. So we're only really getting half the graph. What we need to do now is reverse the power supply. By reversing the power supply, we're now going to get negative potential differences. And now we're going to repeat the process before of recording the potential difference and the current, and then using the variable resistor to change the potential difference and repeat. So once we've done this now, we're going to have many data points for both positive potential difference and negative potential difference. So now all we need to do is plot a graph of current against potential difference. And this, of course, was the aim of the game. When we go back to the question to reread it to check that we've got everything down, you can see that we were asked to describe an experiment that would find the IV graph of a light-emitting diode. We've done that here. So you see there's a lot of points we can say here. In these 6-mark questions, we don't want to limit ourselves just to saying 6 points. In any other question, that's a fine method, but these 6-mark questions, instead we're being marked slightly differently. We need to make sure that we give as full an answer as possible and not just giving a few points that we'll do at the beginning of the experiment. We make sure that we talk our whole way through from the beginning, the middle and the end of this experiment, and we talk about any apparatus and measurements that we need to take. So there we are. This would be our perfect model answer. This is a very common question, so by all means, get writing this down and get learning this. A bouncy ball of mass 50 grams is dropped from a height of 1.1 metres at a point A onto the floor at point B. The path it takes is shown below. We're now told that gravitational field strength is equal to 9.8 newtons per kilogram, and we're asked to calculate the gravitational potential energy of the ball at point A. So let's just label this diagram. We can see that there's a height above the ground of 1.1 metres, and we're being asked what the gravitational potential energy is at that point where it's 1.1 metres above the ground. So the equation that we need to use is gravitational potential energy equals mass times gravitational field strength times height. Well, we're given the mass. We're told that the mass is 50 grams. However, in physics, we don't want to use grams in the equations. We need it to be in kilograms. This means we need to know how to convert grams to kilograms. And we do that simply by dividing through by 1000. Gives us 0.050 kilograms. Now we've got the information we need to put it into the equation. So we can say gravitational potential energy is equal to 0.050 times 9.8 times 1.1. Now putting that into the calculator, I get 0.539 joules. And that is our gravitational potential energy at point A. In B, we're asked to state the gravitational potential energy at B. Now B is on the floor, so it has no height. Even the fact that this says state, not calculate, it tells me that this is going to be a relatively straightforward answer. Because the height is 0, the gravitational potential energy is also 0. It doesn't have any. So all we need to do is write down 0. We have no need to calculate anything. So now, in a similar way, we're asked to state the kinetic energy at point B. So at point B, all of the gravitational potential energy it had at A would have been converted into kinetic energy, because of course there's no gravitational potential energy left by the time it gets to point B. Again, there's a little bit of a hint in the fact that it just says state the kinetic energy. It doesn't say calculate. So for that reason, all we need to do is to take the gravitational potential energy we calculated for point A and say that's exactly the same here for the kinetic energy at point B. So it's 0.539. Next up, we're asked to calculate the velocity of the ball at B and to include the correct units in our answer. Well, to do this, we need to remember what the formula is for kinetic energy. Kinetic energy equals half times by mass times by velocity squared. So we've already worked out what the kinetic energy is at point B. We stated that that was just equal to 0.539. So we can substitute that value into this equation. So here we've got kinetic energy equals a half times by the mass, which we said was 0.050, times by the velocity squared. And that's what we need to find in this question. So we're going to have to rearrange this. To get velocity squared on its own, we're going to take the 0.539 and divide it by a half times 0.050. We're undoing that times that connected it to velocity squared. So popping that into the calculator, I get 21.56. To get the V on its own though, because don't forget that was just velocity squared, not velocity, we need to square root the 21.56. Now putting that into my calculator, I find that the velocity then is equal to 4.64, and of course we need to write down the correct unit. Because this is a velocity, it's going to be meters per second. So now we're on to part E. We're told that when the ball rebounds, it doesn't reach its original height. The maximum height it reaches is point C. Suggest why. So to be able to answer this, we need to remember that in reality, not all of the kinetic energy is going to get converted to gravitational potential energy. Some energy will get dissipated to the surroundings in the most likely form of thermal energy. So that is what we need to understand in these questions, and this could come up in lots of different energy type questions. We just need to understand that energy is often transferred to different forms. The electricity produced in power stations in the UK has an alternating current. It's transported from power supplies to homes where it's used in the mains electrical supply via the national grid. However, batteries used in the home provide a direct current. Here we're asked to describe the difference between a direct current and an alternating current. Now this is a pair of really important definitions, so if you don't know them already, then now's the time to make a note of them. A direct current is a current which will only flow in one direction. And like the question told us, batteries are an example of a power supply that uses a direct current. Now, alternating currents, on the other hand, are currents which regularly change direction. And again, like the question tells us, the national grid and the mains electricity power supply is an example of a power supply that has an alternating current. So those two definitions are very important. In this question, you'll get 1 mark for each of them. If you don't know them, then now's the time to pause the video and write them down. So, next up, in the UK, the mains electrical supply has specific frequency and potential differences. Here we're asked to complete the table. Now this is purely a recall question, okay? We need to know that the frequency of the mains electrical supply in the UK is 50 Hz, and the mains electricity's potential difference in the UK is 230 volts. Now, just like the definitions of direct current and alternating current, these are just simple facts that we need to know, and the only way we're going to learn them is by making a note of them and making an effort to get them in our heads. So if you don't know them, now's the time to write them down. Plugs connect devices in the home to the mains electrical supply. So here we have a nice diagram of a plug. We're told that plugs are designed to ensure electricity can be used as safely as possible. And here we're asked to name 2 of the features of a plug that is designed to increase their safety. Now there's a lot of things we can say here. We can mention the fact that we have an earth wire. We could mention the fact that we have a fuse, which is just here. We can mention the fact that we have this outer plastic insulation so that when we touch the plug, we're not touching any of those cables. We can also mention the fact that the wires themselves are colour-coded so that we can look at them and tell which one is the live wire, tell which one is the earth wire. The final thing we could mention is the fact that we have a cable grip, which is this bit just here, which is going to prevent the wires within the plug from becoming loose. And those are a good 5 different options that we could say that would make sure that we get our marks. Exposed wires are an immediate safety hazard. In the event of an exposed wire, the appliance should not be connected to the main supply until it's repaired. Here we're asked to explain why an exposed wire could cause a person to get an electric shock. So this is a 4-mark question, so they're asking us to be quite specific in the points here. Now I'm going to write down a few options that you can say, 5 different marking points, and any 4 of these would get us our marks. So the first thing that we can say is quite simply, if it becomes damaged in this way, then the live wire may become exposed. And it's the live wire that is the dangerous wire. So if we say something now specific about that live wire, the potential of the live wire is 230 volts. Now the person who might touch this wire and become exposed to this live wire is only going to have a potential of 0 volts. And this is where the danger comes in. because what we have now is a large potential difference between the live wire and the person. Now, when we have this large potential difference between the live wire and the person, what we can see is a current or a charge pass from the live wire through the person's body. And of course, this is what can lead to that electric shock that the question is telling us about. So you can see this is a 4-mark question explaining why an exposed wire could lead to someone getting an electric shock. And here you can see I've written down 5 different points that would each get us one of those marks. So if you missed one of them, that's fine, you're still going to get full marks. But I think this is a really good explanation to learn in case you were to get a 4-mark question asking us about the dangers of exposed wires. Hinkley Point is a nuclear power station. In 2020, 45 terawatt-hours of UK energy was generated via nuclear energy. This is 15% of total energy generation. Here we're asked to calculate the total energy generated in the UK in 2020. So the first thing I would do here is I would just say that 15% is equal to 45 terawatt-hours. Now this question isn't like a physics equation, this is just a math skills question. We need to go from 15% up to that 100%. Now the way that I like to do this is I like to go down to 1%, and I would do that by dividing both sides by 15. That tells me that 1% of energy production was equal to 3 terawatt-hours. Next up now, I can see that 100% can be found by multiplying the 1% by 100. And so I'm going to do the same with the 3, and I'm going to times that by 100. So that then gives me an answer of 300 terawatt-hours. And that is the answer. That is the total energy generated in the UK in 2020. The nuclear fission of 1 kilogram of uranium releases 8 times 10 to the 13 joules of energy. Here we're asked to calculate how many kilograms of uranium are required to provide 45 terawatt-hours of UK energy. And we're told that 1 terawatt-hour is equivalent to 3.6 times 10 to the 15 joules. So the first thing that I would do here is I would work out how many joules of energy is 45 terawatt-hours. Now I can do that just by timesing the 1 terawatt-hour by 45. So 45 times 3.6 times 10 to the 15 joules is going to give us 1.62 times 10 to the 17 joules. And that is the amount of joules of energy we need. So now we need to have a look back at the question, and we know that 1 kilogram of uranium releases 8 times 10 to the 13 joules. Here we need to see, well, how many kilograms are we going to need to get this 1.62 times 10 to the 17? And the way that we will do that is by dividing it by 8 times 10 to the minus 13. Now that gives me 2,025 kilograms. So that is the number of kilograms of uranium that we need to provide 45 terawatt-hours of UK energy. The graph below shows how a radioactive sample of uranium decays over time. We're told the graph can be used to find the half-life of uranium, and we're asked to use the graph to find the half-life. So to find the half-life with a graph, you need to look at the maximum point it reaches on that graph. So here you can see it goes up to 100. Then you halve that value. So halving 100 gives us 50. We read along horizontally until it hits that curve, and then you read down. Then you read what it is on that time axis. I can see that this is 4.5. Now it's not just 4.5 though, because on the axis you see that the time is measured in billions of years, which means that the half-life of uranium in this case is going to be 4.5 billion years. So just to recap there, if you're ever asked to find the half-life of a graph, look at that maximum point that it reaches on the y-axis, halve it, read along horizontally until you hit the curve, and then finally you just read down to the time axis, and that time is going to be your half-life. Radioactive materials such as uranium are hazardous. Nuclear power stations such as Hinkley Point must take precautions to ensure that their staff are safe. Here we're asked to describe 2 ways to minimise the hazards caused by working with radioactive materials. And to this particular question, there are actually lots of different options. You can see here the question just asked for 2 though, so I'm going to tell you a load and then you can pick your best 2. So our options include wearing protective clothing. We can also wear face masks. Now, protective clothing will stop the radioactive materials getting on your skin. Face masks will prevent you from breathing them in. We can also limit exposure time, because the less time that we're going to be in the presence of radiation, the less radiation dose we will get. We can also use tongs, for instance, to handle the radioactive materials. That again is going to prevent contact with our bare skin, a really important factor that we could even state as a point alone when we're trying to protect us from radioactive materials. Now, another consideration could be to ensure that whenever we're not using these radioactive sources, we keep them shielded. So that could be, for instance, keeping them in a lead-lined box when we're not using them. Anything that's going to prevent people being exposed to that radioactive material when not in use. And the final point that we could say is that we should monitor exposure. Now, we can do this with detector badges, which will show when a person has been exposed to too much radiation. So we can keep an eye on it and make sure that we ensure that someone is removed from the environment if they have too much exposure. Now, as this question just wanted 2 ways to minimise hazard, any 2 of those points are going to get you the marks, so get learning them. Okay, so now we're told that research is constantly being carried out on the effects of radiation on humans. Here we're asked to explain why it's important that this research is shared. Now, this is a question that could apply to any part of physics. We need to understand that we need to share our research so that we can peer review the research. So that's what I'm writing here, so that they can be checked by peer review. And what that means is that other scientists can look at it and evaluate it and decide what's valuable about it, if there's any mistakes, and ultimately they can build up the research and improve upon it. So that's why we always share our research in science, so that we can check our research by peer review. The national grid transfers electrical energy from power stations to homes and factories. Transformers are used in the national grid, and the national grid is shown in the diagram below. The different parts of it are labelled A to E. Here we're asked to write the correct letter in the box to identify a step-up transformer. In this case, B is the step-up transformer. We should know that the step-up transformer is always placed between the factories and the national grid, because what it's going to do is step up that voltage to much higher levels for transport along the national grid. Next up, we want to identify the step-down transformer. Now in this case, that is transformer D. We always find step-down transformers after the national grid and before homes. And the whole point of them is to step down the voltage so that it's at safer levels ready to go into our homes. Explain the importance of step-up and step-down transformers in the national grid. So this question, very common, really straightforward in what you need to say. So if you don't know these answers, then when I've finished, pause the video and make a flashcard on it. Okay, so first up, let's start with a step-up transformer. So there's any 3 things out of what I'm going to say you could say to get marks in this question. The first thing we want to state is that a step-up transformer increases the potential difference. Then we also want to state that the knock-on effect of this is it decreases the current. Now we want to understand why this happens. So the whole point is that it's going to reduce thermal energy transfer to the surroundings. Now the whole point of this is to increase efficiency and to make sure as much electricity as possible gets from those factories to the homes. So there we have 4 potential things we could say about step-up transformers. Because this is a 5-mark question, we want 3 to come from step-up transformers and the final 2 to now come from step-down transformers. So we should know that the whole point of a step-down transformer is to decrease the potential difference and therefore to increase safety. We do not want to see the high voltages that we see in our national grid, in our homes. We want it to be 230 volts. Okay, so summarising, a step-up transformer increases potential difference, so up means increases the potential difference, whereas a step-down transformer decreases potential difference. And the whole point of a step-up transformer is to decrease the current, reduce heat loss, and increase efficiency, whereas a step-down transformer is all about making things safer for our homes. Transformers are also used in many other applications, including audio systems. A transformer was used to decrease the potential difference from a 230 power supply to a 24 volt required by a low voltage speaker. The current in the speaker is 8 amps. Assume that the transformer has 100% efficiency. Explain why it's unlikely that in reality it does have 100% efficiency. So the reason for this is that in reality, energy is usually dissipated to the surroundings. We could say that the energy gets wasted. Now the most common way that this is transferred to the surroundings is via thermal energy. So that's why it doesn't have 100% efficiency. Now we're asked to calculate the current of the power supply. And we're given this equation. It's going to be potential difference across the primary coil times by the current in the primary coil equals potential difference across the secondary coil times the current in the secondary coil. And I've written this here in the IV notation just because it's easier to write, and it would be much easier for you in your exams to use that notation as well. Now let's not forget that the primary coil is the first coil, the one attached to the power supply, and the secondary coil is that second coil attached to the speaker. If we think of what information we've been given already, we know that the input voltage is 230 volts, so that would be Vp. We know that the secondary coil has 24 volts, so that would be Vs. We know that the secondary current is 8 amps, so that would be Is, and we need to find Ip. So if we rearrange this equation to get Ip as the subject. Here, first off, by substituting in the values we know, we have Ip times 230 equals 8 times 24. Ip is therefore going to be equal to 8 times 24 divided by 230. Now that gives me an answer equal to 0.835 amps, and that is going to be the answer to this. Current of the power supply is 0.835 amps. So here we're asked to calculate the energy transferred to the loudspeaker if it's switched on for 2.5 minutes, and we're asked to include a correct unit. So because in this question we're asked for energy transferred, let's remind ourselves of the equation for this. Energy transferred is equal to current times by the potential difference and then times by time. So I'm just writing it in the symbol notation just because it takes up a bit less space. So the reason why we're picking this is because we know currents, we know voltages and we know time. So this is the logical equation for us to use here. Now we're asked to calculate energy transferred to the loudspeaker. Either we can use the current in that loudspeaker of being 8 amps and the voltage being 24 volts, or because we do have that 100% efficiency, we also could use the current that we just calculated, the 0.835, or we could use the voltage of 230 volts from the primary coil. We can only do that though because of this 100% efficiency that we're assuming. So the time taken is 2.5 minutes. Now we should know that in physics, our time always needs to be in seconds. So we can convert minutes to seconds by multiplying the 2.5 by 60. That gives me a time equal to 150 seconds. So doing my calculation now, I can say that my energy transferred is going to be equal to, let's say, 8 times 24 times by 150. Or you could do 0.835 times 230 times 150. So popping this into the calculator, I end up finding that we have an energy equal to 28,800 joules. And of course they asked us to include a correct unit. That would indeed be the joules. If you were feeling fancy, you might have ended up giving your answer as 28 0.8 kilojoules. However, I probably wouldn't do that unless I was asked to in an exam, because you're opening yourself up to making mistakes, converting it incorrectly. So I would just get my calculator value and then recognise that energy is measured in joules. So that's our answer. The graph below shows the heating curve for water. It shows how the temperature of water changes as the energy absorbed increases. We're asked in this question to write down the value of A, which is the temperature. So to answer this, let's just evaluate this diagram, okay? So you can see that X is found at negative temperatures. And because it's negative temperatures, it means it's very cold. Now that to me tells me that X is actually ice or solid water. Y therefore is going to be liquid water, and Z is going to be gaseous water or steam. So by recognising those different states, we can see that it's when Y changes to a gas, that's the temperature that we're looking for. And we should be familiar with the fact that water boils and changes to gas at 100 degrees C. Here we're asked to explain what the horizontal regions on the graph show us. So I've included this diagram here for us to look at. So here are the horizontal regions we're being asked about. Now notice that those horizontal regions, the temperature is constant. The temperature isn't increasing at all at those points. The reason why the temperature is constant here is because these are the points where we get changes in state. Now this means that we're going to have the energy being used to overcome the intermolecular forces of attraction between the particles. Now this means that the energy isn't being used to increase the temperature of this substance. The energy is just going towards overcoming those forces of attraction. Now this question here is a 2-mark question. So to be able to get those 2 marks, we need to state 2 key points. I think the most important of all these options is the fact that there are changes in state. We should just understand that of the horizontal regions. But then any explanation as to why the temperature doesn't increase would be your second point. So either we could say energy is being used to overcome the forces of attraction between those particles, or we could say that their energy is not being used to increase the temperature. Either of those can get you your second mark. So now we're told that the water is in different states at points X, Y and Z on the graph. In each of these states, the water has a different density. Here we're asked to explain the differences in the density between the states found at points X and Z. Well, from earlier, we evaluated that X must be a solid because it's very cold temperatures, whereas Z is the gas. Now, any changes in their density are going to be due to these different states. So we can state that Z, the gas, is less dense than X, the solid. That's our first statement that we can make. And now we can get on to explaining why that is the case. So because Z is a gas, the particles are much more spread out than they will be in X, the solid. And therefore, what would be essentially the same mass of this substance is going to occupy a much bigger volume. And that's what's going to have that knock-on effect on the density. So this question is a 3-mark question, so we need to have those 3 points to get our 3 marks. The first thing we want to state is, of course, that Z is less dense than X. Just lay that out to begin with. Then we need to express that in the gas, the particles are more spread out. And then finally we conclude linking it back to density, which is of course mass over volume, and make it clear that although we have the same mass, in the gas it occupies a much bigger volume, which is why it has a smaller density compared to the solid. The density of solid water ice is 916.7 kilograms per metre cubed. calculate the volume of a 2 kilogram block of ice. So this is a calculation question. We need to write down the equation that's relevant. Here we're being asked about density and volume. So that means we're going to use the equation that density is equal to mass over volume. I always like to lay out the information they give me in the question too. So I've written down what the density is and what the mass is so that it's nice and neat and tidy. So now we know density is mass over volume. Now we need to find the volume. Now to do this, we need to rearrange the equation. Now you may be super comfortable with that, but if you're not, remember you can use the triangle. In this case, the triangle has mass on the top and density times volume on the bottom. The way they work is we cover up what we're looking to find, in this case the volume, and look at the triangle to see what the formula will be. So because it's m over d, the volume is equal to mass over density. So that's equal to 2 over 916.7. So there we are now, we've got our calculation. We just need to put that into the calculator, and that gives me 2.18 times 10 to the minus 3. Or you could give it a 0.00218. There you are, that is question D. The specific heat capacity of water in state X, Y and Z is given in the table below. Here we've got a nice table summarising everything, and we're told that the specific latent heat of fusion is 334,000 joules per kilogram, and the specific heat of vaporisation is 2,260,000 joules per kilogram. Now this question simply asks us to describe the difference between specific latent heat and specific heat capacity. So to be able to do this, really we just need to state the definitions of each of them. So let's see if you remember those definitions. If you don't, then pause the video after I've written them down and make a note of them yourself so that you're not wasting any time and you've got them down and you can get learning them. Alright, so let us get started with writing down the definition for the specific latent heat. So specific latent heat is the energy required to change the state of 1 kilogram of a substance. And that is the definition you need to know. You might hear the specific latent heat of fusion or vaporization, but that is just looking at specific state changes going from solid to liquid or liquid to gas. So now let's look at specific heat capacity. Specific heat capacity is defined as the energy required to increase the temperature of 1 kilogram of a substance by 1 degree C, or you could say by 1 degree Kelvin. That is the definition that we need to know for specific heat capacity. It's a little bit longer than specific latent heat because we're talking about a specific temperature increase rather than just a change in state. But I think it's quite memorable, it's quite logical. Both definitions are referring to 1 kilogram of a substance. It's just that specific latent heat is looking at the energy required to change the state, whereas specific heat capacity is looking at the energy required to increase the temperature by 1 degree C. A beaker was filled with 200 grams of 25 degrees C liquid water and placed over a Bunsen burner. Here we're asked to calculate the total energy required to boil all of the water in the beaker. Now this is a clever question, okay? Total energy required. We need to consider here that we need to increase the temperature of that 25 degrees C liquid up to 100 degrees. Then we're being asked about boiling it all as well. So as well as increasing the temperature from 25 degrees C to 100, we also need to work out how much energy we need to boil 200 grams of water. So to change the state from liquid to gas. So it's a sneaky question, and I think it'd be very, very easy for students to miss that final step. So let's have a think about this then, okay? Let's first start with working out the energy needed to increase the temperature from 25 to 100 degrees C. So the equation for this is that the heat energy equals mass times specific heat capacity times by the change in temperature. And that's the equation that I've written down here. So to get that energy, we need to have the mass. Now we have 200 grams of water, but we need to convert that to kilograms. So dividing by 1,000, we get 0.2 kilograms. We then need to have a think about which specific heat capacity to choose. Now, because we're talking about liquid water, and we know that Y is referring to the liquid state from earlier, we can say that the specific heat capacity for this question that we need to use is 4,186. So now we need that change in temperature. Now, we know we need to go up to 100 degrees C to boil it, and it's currently 25, so that means that the change in temperature is 75. So that means that the energy transferred is going to be 62,790 joules. So we've done the first part of the question now, and we have some marks for doing that. Now we need to work out how much energy it will take to change the state of 200 grams of liquid to gas. So in this case, the energy is equal to mass times by specific latent heat. And earlier we were given two different specific latent heats. We were told the specific latent heat of fusion or of vaporization. Now, because here we're talking about boiling the water, that means that we need to use the specific latent heat of vaporization, because that is looking at the state change between liquid and gas. So the value of that we were told on the previous page is 2,260,000. So that's the value we're going to use in place of specific latent heat here. So the energy is going to equal 0.2, because we have 0.2 kilograms of water, times by 2,260,000. Now that leaves us with an answer of 452,000 joules. So here we have our two different sections of energy that we need. We know the energy needed to raise the temperature 100, and then we know the energy to change the state of it all to gas. So what we need to do finally to get our final answer is we need to add these two together. So adding these two together gives me 514,790 joules. So that there is our final answer. That's a really clever question. So if you get something like this in the exam, now you know exactly how to handle it. Nuclear fission and nuclear fusion are two possible methods of generating energy that does not involve the use of fossil fuels. Almost 20% of all electricity in the UK is generated using nuclear fission. Nuclear fission takes place in nuclear reactors like the one below. Here we're asked to use the diagram to help us explain how nuclear fission generates electricity. Do not include details of nuclear fission in your answer. So here what we need to do is to understand, well, how does this nuclear reaction cause electricity to be made? And the key bit is here. So we should understand that nuclear fission releases thermal or heat energy. Now that heat energy is going to be used to heat up the water. Now this water, when it gets hot, is eventually going to boil and turn to steam. Now steam is of course gaseous water, so that gas will be able to rise up, in this case, into that secondary loop in the diagram, and as a result it is going to turn the turbines and the generator, and that generator will make electricity. Now those are our three key points that we need to say in this question to explain how nuclear fission generates electricity. So let's recap all of this information now. So we should recognise that this reaction releases thermal energy, which turns the water to steam, and that steam will then turn the turbines or the generator, generating electricity. Control rods are present in nuclear reactors to absorb neutrons. In the event of an emergency, the control rods can be fully inserted into the reactor to stop the process of nuclear fission. Here we're asked to use our knowledge of the process of nuclear fission to explain how this would stop the chain reaction. Now this is a vital emergency stop mechanism. Here, let's have a think about what the process of nuclear fission is and how it is that this control rod is going to be able to stop the chain reaction if we fully insert it. So these are some of the points we can say to get 2 marks. Any 2 would get you the marks. We should understand that nuclear fission releases neutrons. That is going to be our first point. We should understand that these neutrons that get released would normally go on to be absorbed by more uranium and it would cause more fission. That's our chain reaction that we have there. However, in this case here, this event of an emergency where we fully insert these control rods, the neutrons will be fully absorbed by the control rods in this case. So our third mark that we could write down would be expressing the fact that the neutrons get absorbed by the control rods. So the fourth marking point that we can say to get our fourth point would be that there's going to be fewer or maybe even no neutrons available now. And this is of course because they've been absorbed by the control rods. So we can say here that there's no more neutrons available to cause more nuclear fission. And then we can finally conclude with the fact that control rods stop the fission or the chain reaction. So because this is just a 2-mark question, we've only got to express 2 of these points, which really makes the question quite simple because there's so many options that we have that we only need to write down 2 of them. So this here though is a very full answer. So by giving you all of these potential points now, you're prepared for a much bigger question on this. They could give you a 5-mark question and you'll be able to absolutely smash it now. Okay, so let's look at the next question. So here we're told that uranium-235 and plutonium-239 are the most used nuclear fuels for nuclear fission, and we're asked to explain this balanced equation for nuclear fission. So the trick with these is to look to the top numbers and make sure that they're balanced, and then we'll do the same with the bottom afterwards. So here I can see I have 235 plus 1 in the reactants. And then in the products, I have 144 plus a mystery number, the one that we're asking to find, plus 3 times 1 because we have 3 neutrons. So now we can tidy this up. 235 plus 1 is 236. 144 plus question mark plus 3 times 1 is 3. Of course, the 144 plus the 3 gives us 147. So now we're simplifying this further. We now have 236 is equal to 147 plus our mystery number. Now by simply rearranging this and subtracting 147 from the 236, we end up finding what that mystery number is. We find that it is equal to 89. So we can complete that part of the equation now, fill it in with an 89. So now we've balanced the tops, we need to do the exact same process to the bottoms of this equation. So balancing the bottom now. I can see here that on the bottom numbers, uranium's bottom number is 92. So I'm going to write 92 plus the 0 is going to make the question mark, the mystery number that we need to find this time, plus 36 plus 3 times 0, because again we have 3 of those neutrons. Well, 92 plus 0 gives us 92, and 36 plus 0 essentially is just 36. So our mystery number is going to be 92 minus 36, and that ends up giving us 56. So we can complete our equation now with a 56 as the atomic number of barium. Although both nuclear fission and nuclear fusion generate electricity, only nuclear fission is currently used in reactors to generate electricity. However, in 2022, scientists made a huge breakthrough in their work towards finding a way to use nuclear fission in reactors. For the first time in over 70 years of research, they were able to generate more electricity from a nuclear fusion reaction than was required to initiate it. Here we're asked to compare the processes of nuclear fission and nuclear fusion. So really here we need to remind ourselves of what is going on with nuclear fission and what is going on with nuclear fusion. So let's get started with fission. So nuclear fission involves the splitting of a heavier nucleus into a lighter nuclei and some neutrons. And this is the process currently used in our power stations to generate electricity from nuclear fuel. So we carry out nuclear fission. So next up we've got nuclear fusion. Now nuclear fusion involves the joining of 2 lighter nuclei into a heavier nucleus. And that is the difference between fission and fusion. Fission involves the splitting of a heavier nucleus into lighter ones, whereas fusion's essentially the opposite. It's the joining of two lighter nuclei to form a heavier nucleus. Now we're asked to suggest why nuclear fusion requires such a large amount of energy to initiate. So to answer this, let's remember what we said nuclear fusion was. It's the joining of two lighter nuclei to form a heavier nucleus. Now if we visualise that, we've got our nucleuses. They're both little positive nuclei, and we're trying to join them together. As we can see here, they're both positive particles, aren't they, the nuclei? And because they're positive, we should know that positive or any like charges will always repel each other. And so the reason why we need such a large amount of energy to initiate nuclear fusion is because we need energy to overcome the repulsion between these positively charged nuclei. And there's our answer. All charged particles and objects have electric fields around them. Here we're asked to describe what an electric field is. So another classic definition that if you don't know, then this is the perfect opportunity, there's no time like the present, for you to write down this definition. So an electric field is a region where charge experiences a force. And that's all there is to it. It's quite a simple definition, but it's one we definitely need to know. So the diagram below shows a negative particle. We're asked to draw arrows around the negative particle to show electric fields surrounding it. So because this charge is a circle, we're going to have a radial field. Now all of the arrows are going to be pointing towards the negative because electric fields travel from positive to negative. Now when drawing these field lines, let's make sure that they're evenly spaced, or at least by eye evenly spaced. And the reason for this is that around this spherical charge, if we're at an equal distance away from the charge, the force experience should be the same. So those equally spaced field lines represent that field being of the same strength. So there's the two key things that we need here. We want to make sure that the lines are evenly spaced and pointing inwards to this spherical charge. And I guess one final tip to give is don't just draw like 2 field lines or something. Make sure you draw at least 5 field lines in any question like this, otherwise they may not give you the marks. Here is an electric field diagram between 2 parallel lines. Explain how the diagram shows that the field is uniform. And this kind of calls back on the previous question and how I said about the importance of these evenly spaced lines. So here in this particular diagram, the reason why this field is completely uniform is because the lines are completely evenly spaced throughout. So now we're told that electric fields are responsible for the effects of static electricity. Static electricity has many useful applications, including using it to spray an even coat of paint onto cars. So here you can see that the car is connected to a negative electrode and the paint spray is connected to a positive electrode. Here we're asked to explain how this ensures that the car is evenly sprayed with paint. And this is a 5-mark question, okay? So we want to be very thorough in our answer. So the first thing that I would state is that all of the paint particles are going to have the same positive charge. Now we should know in physics that when we have the same charge, they're going to repel each other. Remember that opposites attract and like charges repel. So as a result, these paint particles are going to repel each other. Now, the direct impact on that is that the paint particles are now going to spread out. And this is going to have the direct impact of us having an even coat going forth onto the car. We're not going to get like big clumps in one area. No, it's going to spread out nice and evenly. So now, if we remember the diagram, the car is going to have the opposite charge to the paint. Now that's really important because, like we said, we understand that like charges repel and opposite charges will attract each other. So in this case, those positive paint particles is going to get attracted to the negative car. Now, the importance of this is that we're going to ensure that the whole of this car is going to get covered in paint. It's not just going to be one of the surfaces, no, it's going to be the back, the front, all of it. All of the little hidden areas is going to get covered in paint because of that attraction between the positive paint particles and the negative car. So here we've got 6 different significant points. The question was only a 5 marker, so we only needed to state those down to get our 5 marks. However, none of them were particularly complicated. I think you could see that those points all tell quite a story. And in the long mark questions, always imagine that you're almost telling a story. You want to start right at the beginning and then you want to get to the end. So let's have a look at the next part. As well as having many useful applications, in certain situations static electricity can be dangerous. Here we're told to state one dangerous situation that can arise from static electricity. So this could almost be considered a bit of general knowledge. I think you could probably get 1 mark with your general knowledge, or of course we've learnt a few. So one example is lightning. One example is that it could cause an explosion. And also another thing is that it could potentially ignite flammable materials. Now, if you've got another great example that shows the dangers from static electricity, then by all means write that down. The mark scheme will allow for anything that is correct, but these are the 3 that you'll be familiar with from learning in class. So in the exam, if you write down any one of those, you're going to get your mark. An investigation was carried out to determine the relationship between volume and pressure of a gas. A cylinder with a piston was placed in a water bath. A mass was placed on the piston and the volume of gas calculated. This was repeated with different masses to change the pressure. Suggest why we used a water bath in this experiment. So water baths are commonly used in science, and the reason why we use them in any of your sciences is to keep the temperature constant. So in this case, we're using it to keep the temperature of the gas constant, and that's all we've got to write. The results were plotted on a graph. Here you can see them. Here we're asked to describe the results shown in the graph, and this is a 3-mark question, so we want to be quite thorough with it. The first thing I always like to do in these questions is just state what the general trend is that I see before I sort of zoom in on it and look in a bit more detail. So I can see that as the pressure increases, the volume decreases. Now that's the initial thing I can say. I can see that it's a bit more complicated than that, but that's always a good starting point in these describe questions. For the second point, I would sort of zoom in a little bit more at a certain section, and I can see that if I look at lower pressures, any increase in pressure has a much bigger effect on the decrease in volume compared to at higher pressures. Obviously, you could say the opposite as well. You could say that at higher pressures, an increase in pressure has less of an effect on the temperature. Anything, so long as you're being much more specific with what's going on, and you're going to get the marks there. Now, the final mark we can say here is just to state what the relationship is between volume and pressure. And we should be familiar with the fact that volume is inversely proportional to pressure. And that really just links back to that initial point, as one of them gets bigger, the other one decreases. That's what inverse proportion is. However, because this is a 3-mark question, we want to state that here as well, okay? So here we've got our 3 marking points. First, just state the general trend. Second, be a bit more specific with a certain pattern that we see. And then finally, make that statement of the relationship between the 2. So there we go, that's that question done. The results can be used to derive Boyle's law. Boyle's law states that pressure times volume is equal to a constant. Boyle's law also tells us that if the volume was changed, the pressure would also change. Explain why changing the volume of a container of gas would change the pressure of the gas. So because this question is just asking us about a change in the volume of a container of gas, we could either talk about increasing the volume or decreasing the volume and follow through the question using that method. Both are going to work. But here let's consider if the volume decreases. So if we decrease the volume and essentially close the walls in on this gas, we're going to see more frequent collisions of the gas particles with the walls of the container. Now every time there is a collision with the walls of the container, there's going to be a force exerted on those walls. Now if there's more frequent collisions, then of course in total we're going to see a much bigger force on the walls of this container. Now, a bigger force in total is going to have the effect of a bigger pressure. Now, this is why if we, in this case, decrease the volume of a container, we will see an increase in the pressure of the gas. So these are our 3 key marking points when answering this question. The first thing we want to state is that as the volume decreases, we could give the converse. Here we're saying as the volume decreases, there are more frequent collisions of gas particles with the walls of the container, and each particle exerts a force on the wall of the container when it collides. Therefore, there's a greater force on the walls. So now we're told that when the gas in the cylinder has a volume of 80 centimetre cubed, the pressure is 20 kilopascals. Here we're asked to calculate the pressure in the gas when it has a volume of 150 centimetres cubed. So we've got a couple of pairs of pressures and volumes involved here. Let's call 80 centimetre cubed V1 and 20 kilopascals P1. Here you can see we're asked to calculate the pressure in the gas when it has a volume of 150 centimetres cubed, so let's call 150 centimetres cubed V2. Now the reason why I'm doing this is because we should know that pressure times by volume equals a constant. We're given this equation, and what we can do to make that usable is we can state that P1 times V1, so A pressure times by A volume, is equal to another pressure times by another volume, so in this case P2 and V2. Now P2 in this case would be the pressure of the gas at volume of 150, which is what we're being asked to find. So rearranging this, I find that P2 is equal to P1 times V1 over V2. That gives me 20 times by 80 over 150. Putting that into the calculator, I find that the pressure of the gas is 10.7 kilopascals, and that there is our answer. So this method is how we harness that equation they give us, that pressure times volume equals constant. We can just take the pressure and volume of one set of data equals the pressure times volume of another set of data, and that's how it works. So it works out quite simple, really. I hope that that's making this topic of pressure and volume a little clearer.
Well done for getting to the end of this paper, lovelies. I'm really, really proud of all of your hard work. You can take a well-earned rest now.